Hi, my name is Yash Devabhaktuni. Today I'm going to be presenting my project, Experiments to Find and Propose Ways to Record a Chess Game. This essentially is a extension of the project that I did last quarter on detecting a chess game and recording it. Except if everyone remembers, I was not able to find the white pixels on the white on white pixels. Sorry, the white on white pieces, but I was able to detect most of them. And I also didn't use a robust technique to essentially try to identify the pieces. And in this specific project or this extension of the project from the previous semester, I'd like to use the techniques taught in class. So, for example, for a short recap, right? This is an example of the board that I was able to use detect checkerboard points to detect each of these points and crop out the image and get each of the squares and the pieces inside them from this entire board. So this project assumes that this algorithm has already been implemented to crop out each of these squares. So I'm just going to use each of these cropped squares to apply different techniques to them and identify any movement on the chessboard. So the agenda for today, introduction, auto thresholding is the first algorithm that I'm going to explore, followed by Fourier transform, template matching, and then circular Hue transform. The final circular Hue transform wasn't done as I couldn't really implement it as much as I wanted to, but that was also a stretch goal that I mentioned in the project. And I'm gonna draw a few conclusions from each of these different um, techniques. So again, as an introduction, I'm going to be just analyzing each of the images and coming up with theories to be able to scale the solution to an automated solution that I could possibly come up with. Because in the last project, the biggest mistake that I did was not doing any analysis and focusing on the automation aspect of things. So O2 thresholding, again, this goes back to my previous project, the specific image, right? I was able to use a kernel filter to be able to get each of these to change the contrast and be able to get each of these different pieces and improve the ability of the algorithm to be able to detect each of these pieces. So I apply the imcrop function to extract, say this image from this chessboard and apply the Atsu thresholding algorithm. And this is the image that I get from it. So as you can see, right, this is the chess piece, and this is the lighter part of the chess piece, lighter part of the white background of the chess piece, and this is the darker part of the white background of the chess piece, and that's how the Atsu thresholding algorithm is dividing it. So once I was able to extract multiple different squares from that specific board, right? I realized that the lighting was definitely very off, and I was able to get a thresholding value of 109, 105, 119 for when there is a piece, or 110. And this is kind of an anomaly because this should be a much higher value, the thresholding value, because this specific example is when there's a white piece on a white image, but the lighting is just throwing everything off. And I initially came up with an idea to use clustering to be able to recognize patterns in images that contained specifically um, white pieces with white backgrounds, black pieces with black backgrounds, only black squares, only white squares. But that because of the inconsistent nature of the thresholding itself, I was not able to come up with any algorithms or a clustering technique. So I decided to pivot a little bit. Um, and so my idea now essentially assumes that there is an initial seed square, or a seed or rather a seed image, and we just assume that it's an image populated with pieces, and black pieces are on the left, white pieces are on the right, and only takes a difference between the previous image and the next image, and tries to compare the locations of each of those squares, and not necessarily detect each of the white and black pieces in the initial game or chessboard game itself. Okay, so for example, the sample image that I fed it in was the one on the left, and the first move was white pawn from this location to this location, and I applied the auto thresholding after putting after kernel filtering, just like I did a couple slides ago. And after that, I was able to detect that white pieces on white squares. Um, this is the control structure, which means that there is no change from the previous state of the game to the current state. And when I was able to detect the auto thresholding, it was 166, 165 to 166. And keep in mind that this specific difference or this specific thresholding was done under constant lighting conditions. So the lighting conditions were not changed at all. And only in those cases, the auto thresholding is this consistent between two images. And this is for like white pieces on black squares. And that's what we're going to focus on, because the main focus here is white pieces on white squares, which had a difficult time of being detected. So in this specific difference, right? Um, this was actually the initial location of the piece, and this is the final state of the location from which the piece was moved to the new location, or the pawn was moved to the new location. So the old state is being compared to the new state. So initially there was a piece, and now there's no piece in that specific square. But the problem is there's no difference in the threshold, and that was where the biggest problem was. Of course, there was a difference in the thresholds, because initially it was just an image with a really high threshold, and once the pawn was moved in, the threshold went down, and that's how we know that there was a difference in the state of that specific square. But it's not conclusive, so I would say that this auto thresholding was a partial success and a partial failure. Fourier transform experiments. This is the technique that I used for this Fourier transform experiments. I was able to increases contrast of each of the images, or each of the states of the images, and cropped out only 50% of the squares, and turn them use the FFT function, turn them into their frequency domains, subtracted them in their frequency domains, and then converted them back to the spatial domain and got the mean values. Um, Jumping in. So when comparing these two specific squares or these two specific images, again, these are control versions, which means there hasn't been any state change between the previous image and the current image for these specific locations. This is just an example that I'm trying to demonstrate to understand the process of the subtraction that I'm using right now. There's slight differences between these two images. Notice how this specific image has a change in the vertical direction as well, and the horizontal direction. But here there isn't much of a change in the vertical direction as much as there is here, and that is reflected here. Um, and these two images are essentially subtracted in the frequency space, because it's like removing noise from the image when it's subtracted in the frequency space, and also it's much faster than doing it in the spatial domain. And this is the result of the subtraction that takes place, and then transforming back to or inverting the image back to the spatial domain. This is the mean. This is the image that we get, and the mean value is much closer to zero than not, which obviously makes sense, because when you subtract two images, right, their difference should be zero if they are the same. But unfortunately, they're not the exact same in this particular scenario, because there's usually some sort of resolution difference, or at least a little bit of lighting difference, or even a perspective difference to an extent. So now, taking into account only the changes or the changed locations. So this is the initial or the previous state of the image, and this is the next state of the image. What's happening here for this specific image, right here, is that the this location is being taken and subtracting this specific location from this location, because this is the final state of the image and this is the initial state of the image, and this is producing a mean intensity value of a negative 13.49, which is way far away from 0. And we're taking this and subtracting this from this specific value, specific square or location, and this is all done in the Fourier domain and or frequency domain, and converted to the spatial domain, and that gives an extreme a mean intensity of 83.4146, which essentially shows that there was a difference. And this doesn't actually happen for most of the other images. It's much closer to 0 than not. This is kind of an anomaly, of course, but when you take multiple passes through the box and possibly increase or decrease the cropping of the box, this actually stabilizes to a value or converges to a value that's much closer to 0 than not. And these ones, like this one and the one right here, do not converge to values that are closer to 0. So one can also use majority voting from these multiple passes to detect these changes of locations of the pieces in the image itself. So key findings is that the difference gives image results that can be used to detect pieces, of course, that which I went over. Image differences are greater than 0 in all cases because resolution is different, which was also an issue, and I gave an example of that earlier, even when discussing Atsu. And the biggest drawback is that the mean intensity is just not enough, and we also need to be able to explore feature extraction. And the next technique that I used was template matching, and this one was the one that gave like the most convincing results. Matching the whole image, but the correlation itself was higher because parts of the template image would decrease the correlation score, even though there was no piece in the box because of the opposing colors in most instances. What this essentially means is that, for example, if you take this image into consideration, right, and this is the picture of this specific square in the previous state, and this is the final state of the image. And again, these are control images, which means there was no change of location of the pieces. So, for example, if you take this specific example into consideration, we don't want to take the white space into consideration in order to be able to detect or match the specific template to this, because in this specific case, it doesn't make a difference. But let's say when there is actual movement, it does make a difference if the size is increased and the correlation value is taken into consideration. And also, we're trying to match templates here, not whole images. So that's the other reason why. And secondly, shadows had to be taken into account. Some of these pieces have shadows that fall in each of the squares, and we don't want to take them into consideration when doing the correlation matching. And thirdly, light source played an important role as well, obviously, because even though light source was kept constant, right, we needed to eliminate the dependence on the light source as much as possible. When there's movement, you can see that the final result of a detection is 0.26 when the piece is moved out of the square. When the initial state it has the piece in it, and the final state does not have the piece in it, it's a very low score. But when the same happens for when there isn't a piece in an empty square and a piece is moved into it, there's a slightly higher score. But when all the images were measured, the average score of the control images was much higher. It was approximately close to 80%. Sorry, 90%. The correlation, these are the correlation values for, let's say, 0.577 is for this particular square, and 0.54450506 for this particular square. And it keeps going on. 0.76 for this particular square, as we discussed earlier, and 0.3929 for this particular square. And this was, and I think one of the reasons why this was as robust as it was because of the fact that Normex Core takes into account even the intensities and the angles of the images that are being considered as well. And based on this, it makes a correlation. It gives a correlation percentage between the template and the image. These are the key findings. When the square or box contains a piece, the correlation value is really high. When comparing them, the score is slightly higher. And this is the stuff that I went over as well when comparing empty box template to image with a piece. The score is very low, and this is one of the most foolproof ways to detect a change in the state. And this was my stretch goal, the circular hue transform. In this specific example, I could not detect any circles in this specific image because, for obvious reasons, there isn't much of a circle here to be able to detect here. And so what happened was I was able to change the pieces itself in the image to this pieces like this, in which there's like a circular head for the spawn, for the pawn, sorry. And I had to increase the sensitivity to about 0.98 because it seemed like the contrast was just not good enough to be able to detect this particular circle for the spawn. But the biggest problems with this specific circular hue transform was occlusion, which means I was not able to take the circular nature of this entire pawn into consideration. And also there were no perfect circles um, along this shape of each of the chess pieces. Um, Going forward, based on this idea, sometimes I could detect pieces in the form pieces like this after using a canny edge detector and changing it to a black and white format based on the canny edge detector. But sometimes the detection was extremely unreliable, and I couldn't actually find a foolproof way of being able to detect each of those images. For example, this is the image of a horse chess piece, and it could not detect this particular curve because I think and I'm pretty sure it does not fall on the circle equation x squared plus y squared equals r squared, so, which means all these points are not equidistant from a specified radius, so that's why they don't fall on the same circle, and that's probably why they're not being detected, and instead smaller points like this are being detected. Occlusion, like I said, is the biggest reason. Circular properties of these pieces is being hidden because of that. And obviously, x squared plus y squared equals r squared is the circle equation that's being used to detect each of these circles. Um, but the points on the curve, like I said, right here, are not even close to being on the equation, and that was the biggest problem. Increasing sensitivity, even in this case, or like even when there's when I was able to change it to black and white using a canny edge detector, did not actually help much, and it also takes into account images like these in which there really is no circular shape to be able to detect. So at the end of the day, it only worked for pawns, and that just was not good enough. So I thought this was a failure. And yeah, but yes, those were all my key findings and conclusions based on each of the different experimental techniques that I was able to use on the squares of each of the locations of the pieces and the chessboard squares and